In this lab, you will study standing waves on a string.
The resonant frequencies of a string depend on three factors: the tension, the length of the string, and the mass per unit length of the string. Let's observe what happens to the frequency of a note played on a guitar when we adjust these variables. As I turn the tuning peg, the tension in the string decreases. This causes the frequency of the note to decrease or lower in pitch. Now let's look at the mass per unit length of the string, or how heavy the strings are. As the mass per unit length of the strings decreases, the frequency of the note increases. Lastly, I can vary the length of the guitar string by pressing the string against the neck of the guitar. As I move my finger down the neck, decreasing the string's length, the frequency increases. Now let's derive these relationships mathematically.
For traveling waves on a string, the velocity v is equal to the square root of the tension over the mass per unit length of the string. We can also express the velocity as the product of the frequency and the wavelength. Standing waves are created at resonant frequencies. At these frequencies, the incoming and reflected waves add constructively to create a standing wave.
Different resonant frequencies are called modes. We label each mode with a number n.
The stationary points on the standing wave are called nodes, here marked in red. The points of maximum amplitudes are called antinodes. Combining our earlier equations for the velocity of waves on a string, we find that the frequency is equal to 1 over the wavelength times the square root of the tension over the mass per unit length.
For each mode, the wavelength is equal to 2 times the length of the string divided by n. Combining these equations, we find an expression for the frequency of the nth mode in terms of the length, tension, and mass per unit length of the string. Recalling the guitar earlier, we see that as the tension increases, the frequency will increase, and as the length and mass per unit length increase, the frequency will decrease. When a string is plucked, the modes that are excited depend on where the string is plucked. We will only excite modes that do not have a node at the point where the string is plucked. For example, if we pluck a string at L over 2, we will not excite even modes, as all of these modes have nodes in the middle. In the first part of the lab, you will measure the resonant frequencies for standing waves on a slinky. By shaking the slinky at different frequencies while the opposite end is fixed, we can excite the different modes. Use a stopwatch to measure the period of these oscillations, calculate the corresponding frequencies, and record these into your notebook. In the second part of the lab, we will excite resonant frequencies on a string that is connected to a speaker. The speaker will move up and down, causing the string to vibrate. You can change the tension on the string by changing the amount of mass. The amount of tension is equal to the mass hanging on the string in kilograms times the acceleration due to gravity g. For example, if we hang a 300-gram mass on the string, or 0.3 kilograms, we will find that the tension is 2.94 newtons. You will use the computer to control the loudspeaker's oscillations.
Here you can select the wave shape, the frequency, and the amplitude. Choose sine wave for the wave shape. When adjusting the amplitude, do not set it above 5 volts. You can change the frequency and amplitude while the power amplifier is on by pressing the plus and minus buttons. You can also set the step size of these changes using the left and right arrows. Starting at 0 Hz, sweep through a range of frequencies to find the harmonics. These frequencies will have the largest amplitudes.
This is the first mode, or the fundamental frequency. It has 2 nodes on the ends of the string and 1 antinode in the center. This is the second mode. The node in the center of the string is stationary. You can touch the node without disturbing the standing wave. If you touch any other place on the string that is not stationary, the wave will collapse. Record the frequencies for at least 5 modes. Remembering our equation for the frequency of these modes, how do you expect the modes to relate to each other? How will changing the tension and the length of the string affect these frequencies?